scientists realized that some organic molecules can just not be explained properly by a single Lewis structure. And a good example of that was something like the early finding of benzene. We have a line angle formulas here. It's 6 carbons in a hexagon ring, closed off. And the Lewis structure that was originally proposed showed it with alternating double and single bonds. So we'll see shortly that there's a family of organic compounds called alkenes. And when we talk about alkenes, we're talking about compounds which contain at least one carbon to carbon double bond. And these compounds are very reactive, we find. We find you can react them with things like bromine, and it will decolorize bromine liquid solution as the bromine atoms actually add on across a double bond and produce a new chemical compound. Trouble is that when you take some benzene and try and react it with a classic chemical like bromine for an alkene, it doesn't react, doesn't do anything. So this proposed structure for benzene, which suggested it had chemistry like an alkene with carbon-to-carbon double bonds, didn't seem to fit with the chemistry that was already known. So there was something else going on that the simple Lewis structure of alternating bonds wasn't pointing out. Other information we've got since shows that the carbon-to-carbon bonds in benzene are all exactly equal at 1.4 angstroms. An angstrom is about 10 to the minus 10 of a meter, so it's a relatively small distance, although fairly common for a carbon-to-carbon bond. But that distance is longer than a true alkene carbon-to-carbon bond, but shorter than a true carbon-to-carbon single bond. So if we really have alternating double and single bonds, how is it that we're getting a molecule with all of those chemical bonds being exactly equal? There should be an alteration between double and single bond length. This isn't happening for benzene. So we start to see some of the limitations in using these Lewis structures. And it didn't really become clear until Pauling pointed out his idea of resonance. So what Linus Pauling realized was that some compounds cannot be explained by these simple Lewis structures. And in the case of benzene, he proposed that we have some resonance structures, which are still Lewis structures, some resonance structures which combined give us the complete story about these more complex molecules like benzene. The carbon-to-carbon bond length for each pair of carbons in a benzene ring is indeed the exact same bond length. But we can't use Lewis structures for this. So we have to use a combination of structures, and then we're saying that between these two examples, between these two structures, we see all aspects of the true molecule. And we say, or sometimes round it down to being a resonance hybrid. We show this for benzene with a circle in the benzene ring to try and show that idea that we actually have a delocalization of electrons in the carbon ring for benzene. There are no individual double or single bonds. And the reason for this is because of the sp2 hybridization of each of these carbon atoms in the 6-membered ring. We know that each carbon has a trigonoplanar arrangement of those hybrid orbitals. So for example, this carbon here, 1, 2, 3 hybrid bonds, sp2 hybrid bonds, making that trigonoplanar position. Likewise for this carbon, a hydrogen coming up here, flat with the plane of the board, giving a trigonoplanar arrangement, bond angles of 120 degrees each time. We said that therefore gave each carbon a single atomic p orbital, which wasn't part of that hybridization. Atomic orbital which fitted around the atom by being positioned above and below the plane. And we said that those unhybridized atomic orbitals were often used to form pi bonds between two carbon atoms. Yeah. It's happy. It's going for my eyes, yeah? Jeez. So, we can, and again, I'm drawing my atomic orbitals much smaller than they should be, just to give a bit of clarity. The reality is that this big fat atomic orbital is reaching over and actually overlaps with its neighbouring atomic orbital on the next carbon. But it's not just these two which overlap. These two overlap, as do these two, and these two, and these two, and these two. So there's actually a continuous circuit or series of stepping stones of atomic orbitals overlapping one with the other. So when we try and form these double bonds, these pi bonds, with overlapping electron density, they're not localized between two atoms. Because of the continuous connection of atomic orbitals, one for each of those carbons, that actually gives us a continuous flow of electrons above and below the plane of the benzene ring. So they're not localized electrons in these bonds, they're actually delocalized and form a ring current around the entire carbon ring. So the atomic orbitals have to shuffle together a little bit closer to get better overlap, because of course they are standing on end, not like the hybrid orbitals which come together much more cleanly. So they shuffle closer together, and with the electrons flowing all around the molecule, we get an exact carbon-to-carbon bond length which is equal for all 6 of those carbons around the ring. Now, Lewis structure theory doesn't tell us how to draw bonds which are 1.5 bonds long or intermittent in length between a single bond and a double bond. But what we can show through Pauling's idea of resonance is multiple Lewis structure illustrations, and we can say that the true nature of this molecule is a combination of all of those resonance structures. We know that each of these carbon-to-carbon bonds is intermittent between a double and a single bond, so they have some double bond character and some single bond character. So between the two resonance structures which are being drawn, we can see for any two carbons, part of its character is shown as a double bond, and part of its character is shown as a single bond. So between the two pictures, we see all aspects of this molecule. And this is what these resonance structures are giving us. All the pieces of the puzzle. No single picture is completely right, and no single picture is completely wrong, although there are some aspects which are right and wrong. They're giving us more information. What we're not saying, which often confuses people, we are not saying that these two molecules are in equilibrium with each other. The molecule doesn't actually exist as this. It doesn't exist like this. The true existence of the molecule is somewhere in between those two ideas. We just don't have the ability to draw, normally with Lewis structures, a single structure for it. So each of those resonance structures gives us an aspect of the more true molecule. And sometimes in your textbook you'll see it summed up as this resonance hybrid here. That circle trying to represent the continuous flow of electrons completely around the benzene ring. And there are certainly many other examples of chemistry where we really should be resorting to resonance structures. The carbonate ion, which we might have talked about either yesterday or Tuesday, is another example. All of these carbon to oxygen bonds are exactly equal in length. Through these resonance structures, moving lone pair electrons and pi electrons, we can shift and shuffle the electrons around to show all other alternative forms for the molecule. So we can move a lone pair in from this oxygen to make a double bond, and to keep the octet rule, that pair of electrons has to move out. try that trick again a second time, move another pair of electrons in from this oxygen to form a new carbon to oxygen double bond. Again, something has to give, so there's very much a domino effect going on here. As one new bond forms, another bond has to break. But the only movement of electrons we're performing each time is just lone pair of electrons to make a new pi bond, or breaking a pi bond to turn them back into a lone pair on one of the two atoms it was initially connected to. We see this flow of electrons around. And again, it's not suggesting one or different structures for this molecule. Each resonance structure is showing us a clue and a piece of the greater whole in the true nature. So, not all resonance structures are created equal. Some resonance structures are better than others, and we therefore have to think about some rules for this. First thing, most of the time, the contributing structures must have the same number of valence electrons. And they normally have, therefore, the same number of lone pairs and pi bonds. Occasionally we do break this rule. This usually ends up with a less wet or a poorer resonance structure, or one that's only a minor contributor. So as you're moving from one molecule to the next as you draw them, the number of pi bonds and the number of lone pairs is normally going to be the same each time. They're just juggling and moving them around. As you can see from that carbonate and sulfate example we did on the previous page. If we move a lone pair into being a pi bond becomes a lone pair. So for each individual molecule, there's the exact same number of lone pairs, the same number of pi bonds. And altogether gives us obviously the same number of valence electrons. All the structures should obey the octet rules. It's very unhealthy for an atom to have an incomplete octet. It makes it unstable. This is certainly bad news for structures A and C as we draw them. Structure A, we're drawing the carbon here at the centre with just 2, 4, 6 electrons around it. Only 3 of the 6 electrons under its control, making it positively charged and without a complete octet. That's bad for the stability of the structure, therefore bad for its potential to be a true part of the true molecule. And then the last one here, the oxygen has an incomplete octet as well. That doesn't seem healthy for the molecule. So it doesn't seem like a very good resonance structure. All contributing structures must have all nuclei in the same positions. And that at least we've achieved. We're not changing the connectivity of the atoms in the molecule, because we're just changing and shifting the lone pairs and pi bonds. All contributing resonance structures must have the same number of paired and unpaired electrons, which we've already mentioned. Which is kind of bad news for A and C, because we don't have a pi bond here, we don't have a pi bond here, we've increased the number of lone pairs. Again, just running through these rules. Structures with completed octets are good. Contributing structures with more covalent bonds are more significant than those with less. Again, the same kind of idea as covalent bonds at B, giving each of those atoms a completed octet. Structures which involve opposing charges contribute less than those that don't have those opposing charges. To have a positive charge and a negative charge right next door to each other, that doesn't seem highly likely. It does occasionally happen, but it's not a natural thing to see. Structures contribute more when they show negative charges on the more electronegative atoms, as we said, and positive charges on the less electronegative atoms.